All right, let's dive right in. Today, we're going deep inside your computer, your phone, pretty much every smart device you own, to uncover this hidden battle that's happening literally billions of times a second. We're talking about how we try to squeeze every last drop of performance out of our microprocessors and the giant obstacle standing in the way, the memory wall. You know, it's a question we've all asked, right? We have these processors that are just unbelievably fast, and yet we still see that little spinning wheel. We still have to wait for things to load. I mean, if the engine is a supercar, why does it always feel like we're stuck in rush hour traffic? What's the deal? Well, believe it or not, the answer to that whole mystery is laid out for us right here, in this one visual. This is the battleground. It perfectly shows this constant tug of war between a blazing fast processor and the much slower job of actually getting the data it needs to do its work. So, let's break this whole thing down. Okay, so to really get what's going on, we first need to understand our hero, the processor, and of course the villain it's constantly up against. This whole thing is what we can call the processor's waiting game. So just think of your CPU, the central processing unit, as this genius worker on a factory floor. It's brilliant, it's tireless, and it can perform calculations at a speed that is just mind-boggling. It's basically ready and waiting to just tear through any task you can possibly throw it at it. But here's the kicker. That brilliant worker can't do a thing without the raw materials it needs, the parts for its job. And in the world of computing, those parts are data. And a shocking amount of the time, our super fast CPU is doing, well, nothing. Absolutely nothing. Just waiting for data to show up. So why is it always waiting? Well, this waiting game is caused by something engineers call the great speed gap. And this, right here, is the core performance bottleneck in pretty much all modern computers. It's the real villain of our story. So just how fast is our hero? A typical computation can take something like 16 microseconds. That's 16 millionths of a second. I mean, it's practically instantaneous, an incredible feat of engineering. But that's only half the story. Because, and this is a huge because, when the processor needs to get data from the main memory, the computer's primary storage, it takes around 200 microseconds. That is more than 10 times longer. It might not sound like a lot to us, but in the world of processors, that's an absolute eternity. And you can see that gap visualized perfectly right here. The processor's speed is just pegged to the max, drastically faster, while memory access is just lumbering along at significantly slower. That massive difference is the entire problem. And this brings us to the villain's official name, the memory latency bottleneck. It's really just a fancy way of saying that our super-fast processor is constantly being held back, forced to just sit there and wait for the very data it needs to do its job. So what's a super-fast processor supposed to do? It can't just sit around and wait. Well, instead, engineers have developed a whole bunch of really ingenious techniques to keep it busy, and it's all part of a strategy known as parallelism. The main idea here is something called instruction-level parallelism, or ILP for short. And it's pretty brilliant, really. Instead of doing one thing, then waiting, then doing the next thing, the CPU just tries to do as many things as it can at the same time. If it has to wait for one task, hey, no problem. It'll just work on another one. One of the main ways it does this is with pipelining and superscalar execution. Just imagine a bunch of assembly lines running side by side right inside the processor. Each one of those pipelines can work on a different, independent task. It means several instructions can be in different stages of being completed all at the same time. And if we look back at our diagram, you can see this in action. These different colored streams flowing toward the core, those are the separate pipelines, each one processing instructions at the same time. It's this highly efficient, really organized system for multitasking. Another trick is called instruction packing. Think of it like being an expert at packing a moving truck. You don't just throw things in randomly, right? No, you carefully arrange everything to use every single inch of space. The processor does the same thing, bundling different instructions into one package so they can all be executed at once. Yeah, think of it like this. You have all these different instructions, like these little puzzle pieces, and they're all being funneled down and packed together into these neat, super efficient blocks. This just maximizes the use of all the processor's internal parts so that nothing goes to waste. But, all these parallel tricks are only part of the solution. The processor's single most powerful weapon against this memory bottleneck is a special, ultra-fast, and very small memory that sits right next to it. It's called the cache. And the cache is just incredibly effective. It basically works by guessing what data the processor is going to need next, and it preloads it. And get this, it guesses right about 90% of the time. This is called a cache hit. So for 9 out of every 10 requests, the data is right there, ready to go, no waiting required. The difference between a cache hit and a miss is, well, it's night and day. A hit means the data is found instantly, performance stays high, everything is great. But a miss, that's what forces the CPU to make that long, slow trip all the way to main memory. That's what triggers a stall that can last for over 100 clock cycles. That's the bottleneck in action. So even with all these amazing strategies, we still have to deal with that 10% of the time when the cache guess is wrong. And the impact of that one single miss, that's what we still feel as lag or slowness. That moment when the CPU is forced to stop everything dead in its tracks and just wait for data from main memory, that's what we call a stall. The assembly lines grind to a halt. Our hyperfast worker is just standing there, tapping its foot, waiting for parts to finally arrive. And just look at the scale of the penalty here. The execution speed is lightning fast, right? We're talking 4 instructions per nanosecond, but the memory delay from a single miss, it can be 100 cycles. That delay completely dwarfs the speed of execution. It just wipes out so many of the gains. And the end result is exactly what you see here: heavy stalling and poor compute utilization. We have this incredibly powerful processor, but because it spends so much time waiting, its full potential is just wasted. This is the ultimate cost of hitting the memory wall. Which leaves us with a final, really crucial question. This battle between processor speed and memory access has been raging for decades, and as our programs and our apps and AI models demand more and more data, the central challenge just gets bigger. Can these clever engineering tricks continue to outrun this ever-present memory gap?